Good morning. I'm going to put together a little video here on problems from homework number 15. This is week 5, and this is the third mini video that you should be viewing this week. So homework 15. So we've been talking about radicals and radical expressions. So now we're going to start solving equations, and the equations that you see are going to have a square root in them, or a cubed root, or a fourth root. I want to talk about how we go about solving them. Well, what we need to do is solve this for x here. So we need to get rid of this square root. So the way to get rid of a square root is to do the opposite of square rooting. And the opposite of square rooting is squaring. So if we square both sides of an equation, we end up with the square and the square root cancel. So we just have x on the left-hand side. And on the right-hand side, we have 11 squared, and 11 squared is 121. Now, one thing that we have to do, and it doesn't seem like it's really necessary in this problem, but we want to plug our number back in to make sure it is a true solution. And if we do take the square root of 121, if I put 121 back in for x, the square root of 121 is in fact 11. So it actually works. So when we click our box here, there'll be one solution. So for one solution we click this part. If there was two solutions, we click this one. But for one solution, we put 11 in there. No, 121, 121, and then we check our answer here and give us the green check mark. Okay. Now, the reason why I say that you want to plug it back in is say we had something like this: the square root of x, right, equals we'll say like -3. Okay, and let's say you were just a robot and did whatever Mr. Gardetto said, whatever Professor Gardetto said, you did. Okay, like a good student. Well, if I say that you need to square both sides, then we go ahead and square both sides like a robot. Square this side, square this side. So we end up with x equals -3 squared is 9. Well, it seems like this would be our answer, just like we got x is equal to 121 on the first one. Okay, but this one here, if we plug 9 back in, remember the original equation was square root of x equals -3. If I plug 9 back in, the square root of 9 does not equal -3. Remember, square roots of 9, square root of 9 is equal to 3, not -3. So what we call this is it's called an extraneous solution. It's basically a fake solution. It's a fake solution that sometimes when you square both sides of an equation, you get these fake solutions. There is no solutions to this. There's no solutions to this equation. But by squaring both sides, we got a solution, but it's called an extraneous solution or a fake solution. So you got to be careful to check your answers to make sure you don't have a fake solution. What makes it fake is we have this negative over here. Okay. So let's look at another one here. Okay, so this one here is similar, except for it has an extra little step here. Before we square both sides, before you square both sides to get rid of the radical or the square root, you want to isolate the square root signs. You want to isolate whatever's underneath the square root. So to do that, we need to get rid of this +2, and that's the same as solving an equation. We subtract 2 on both sides. If we subtract 2 on both sides, we get square root of y equals 4. And now we can just square both sides. Square that side, square and square root cancel. Square this side, and you get 16. So let's just check to make sure that's true. Let's plug it back in. When you check, you can just kind of check into your head. Square root of 16, square root of 16 is 4. 4 plus 2 is equal to 6. That checks, and so we can put 16 in the box. Okay. Remember when we check the box here? Let me see if you need to click this. Let me see if we can just put 16 without putting this thing. Let me check the answer here. Oh yeah, it actually gave me the green check mark. It also told me there's an alternate answer, which is in set notation. That's okay. Green check mark's good either way. So found something out there. Let's go to another one here. Let's go to number 6. Okay, seems to be similar. We have a binomial expression underneath the square root sign. That shouldn't really mean too much. We still want to isolate this right here. I want to get that by itself, so I'm going to add 6 on both sides. So my first step does not get rid of the square root sign. The only thing that's going to get rid of that square root sign is squaring both sides. So I get 5z plus 6 equals, and if I add 6 on both sides, I get 11. And then I can square both sides. Square both sides. All that happens on the left-hand side is the square and the square root cancel. So you just write down what is left underneath your radical sign, and just remember to square the right-hand side too. So you get 121, and now you just solve this equation. Okay, if the solution's a fraction, you want to just reduce your fraction to the lowest terms, and I think there's a little fraction button right here. Okay, looks like this one might turn out to be a fraction. Okay, so I'm going to leave that up to you. I think you guys got the gist of that problem. Let's see, 7. Okay, 7. 7's a little different because there's a cubed root. There's a cubed root. Well, we're going to start out the same way. We're going to isolate the radical. We're going to isolate the radical. We're going to get this by itself. So we got to add 1 to both sides. So I'm just going to copy down the cubed root of 8x minus 9. Okay, and I'm going to add 1 to both sides, so that is a 4. Right? Add 1 there, add 1 there. Okay, now, to get rid of a square root, we squared both sides. How do you think we get rid of a cubed root? If you're thinking you cube both sides, you're correct. You just take the third power of both sides. So I'm going to just use parentheses here. So I'm going to take the third power on this side, and I'm going to take the third power on this side. So this third power cancels with the third root. So you get 8x minus 9. And 4 to the third power. Don't you dare multiply 4 times 3 and make 12. It's 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64. And you just solve that equation. I'll leave that for you to do. That was number 7. Number 9. Okay. All right. Number 9. This is when it starts getting a little bit strange. So far, we've talked about that it's impossible to take the square root of a negative number. Okay. And the reason why it's been impossible is because it's not real. Square roots of negative numbers are not real. They don't exist. They don't exist in the number system that we know of. And the number system that we know of and that you know of has been the real number system. That's about to change. There's actually a complex number system that has an imaginary component to it. And so let me explain to you, first of all, why this actually occurs. Mathematicians hate to say that there's the unsolvable problem. Okay, and the most simple unsolvable problem came in existence a long, long time ago, and it was the square root of a negative, right? And I'm just going to say square root of a -1. The square root of a -1 is, or any negative for that matter, is not possible. Okay. However, if you make up a new number system, and this is called the imaginary number system, it is possible to take the square root of negative numbers. And so I'm going to let this square root of -1 be a, well, it's going to look like a variable, but I'm going to make it look a little bit fancy. I'm going to kind of curve it here to make it look like a fancy looking letter of the alphabet. You can see what letter I wrote there. I wrote an I. Now, the reason why I kind of curly Q the 1 is so that it doesn't look, or the I is so it doesn't look like a 1. Because sometimes people don't forget to dot their I's. And if you forget to dot your I's, it looks like a 1. So you kind of make it like this. And this is not a variable. A variable stands for anything. This is actually a number. And I stands for the square root of -1. That's what I is. It's called the imaginary, and this is probably why I is used. It's called the imaginary unit. The imaginary unit. Okay, and it's denoted by the letter I. So anytime you have a square root of a negative number, it's going to be written in terms of I. So what I can do in this problem here is I can break up, just like the last video, I broke up like the square root of 8, and I said 8 was 4 times 2, and we took the square root of 4 and we brought it outside of the radical as a 2. If you recall, the square root of 8 could be simplified into 2 root 2. We're going to do the same thing with the square root of -36, is we're going to break it up into the square root of -1 times 36, because -1 times 36 is equal to 36. Now, what I can do is I can take the square root of 36 and I can bring that number out of the radical. That's a 6. And I can also take the square root of -1, because I know over here the square root of -1 is written as this letter right here. So, and it's common to put the letter after the number, kind of like variables and coefficients. Okay, so we say, to simplify this expression, we say 6i. 6i is what the square root of -36 is. Now, when you click this box, see this I right here? I don't know whether your keyboard I works or this I works. I'm going to tell right now. So I'm going to put 6, and I'm going to use my keyboard's I. So I put an I there, and I'm going to check my answer, and it works. Okay. The other thing that could work is you can actually use the I that's actually on your menu when you click the box. But the keyboard I works the same. See how the I is kind of italicized a little bit? I think that's done on purpose. Okay. It's going to get a little weirder. Okay. It's going to get a little weirder here. Just got to remember, anytime we see a square root of a negative number, Anytime we have a square root of a negative number, it's going to be written in terms of I. All right, that was 9. Okay, so let's look at 11. All right, square root of negative 15. Square root of negative 15. All right, so let me break up 15. Now, 15 is not a perfect square like 36 was, so this is just negative 1 times 15. 15 can be only written as 3 times 5. 3 and 5 are not perfect squares, so the only thing that you can do here is you can take out the square root of negative 1 as an I. Think of it this way. Think of this negative turning over and making an I. That negative right there just kind of turns around and makes the I. I just make it a little bit fancier by putting the curly cues on it. So the I is the only thing that comes out. The square root of 15 is left. So we say I square root 15, and we could use the keyboard, and we can put I in, square root there, and then 15. Okay, you have to use the menu there to make the square root sign. Okay. 14. Let me clear this first. Let's go to question 14. Okay. One thing that you need to do before you do any multiplication is you need to convert the expressions in terms of I. Since we are dealing with imaginary numbers, you cannot multiply the numbers inside the square roots together. This rule here, square root of A times square root of B equals the square root of A times B, only holds true for non-imaginary numbers. So like if you multiply this negative 4 times this negative 1, then you make a positive 4, which isn't imaginary. Okay, and this has definitely got some imaginary solutions. So the first thing we want to do here is we want to take these negatives out as i's. Take these negatives out as i's. So this is going to be a negative 2 I square root 4. And this is going to be a negative 3 I square root 1. Okay. And now we can multiply these numbers together. Negative 2 times 3 is 6. I times I. Well, I times I is I squared. It works the same as like variables as far as exponents go. When you multiply x times x, you get x squared. When you multiply an I times a I, you get I squared. And then square root of 4 times square root 1. Square root 4 times square root 1 is just square root 4, because I can use this property now. I can use that property, so that's square root 4. But square root of 4 is equal to 2. So that's 2 times 6. So that's 12 I squared. Now, let's talk about I squared for a second. Okay, and this is where it's going to get a little bit weird. Remember, I is equal to the square root of negative 1. Okay, you always have to remember that fact, that I is equal to the square root of negative 1. I squared therefore, would be equal to the square root of -1 squared. What do you think happens to this square and this square root? Yeah, they end up canceling each other. The square here cancels with the square root that's over the top of the -1. So I squared actually can be simplified. I squared can be simplified simply to a -1, not a square root of -1. That's what I is. But I squared can be simplified to -1. That's just weird. That's weird. I mean, usually if an answer has an x squared in it, that's as far as you can go. But for this problem here, I can actually go one more step. I can go one more step. I can change this 12i squared into 12 times -1, which is -12. So we don't want to leave an answer with a power that is a square of I. And really, we're going to learn how to simplify other powers of I here shortly. Okay, so when we click the box here, we're just going to put in -12. No I in the problem at all, or in the answer at all. I don't know why I didn't check my answer here. Looks like my program kind of froze up on me. Okay, let's go to another one. No, it froze up. Maybe that's happened to you guys before. It looks like it froze up. So I'm going to remember which problem I just got through doing. I just got through doing 14. I'm going to close this up and start it over. Preview. Okay, that was 14. So I think I wanted to go over 16. Okay. Anything raised to a 0 power is equal to 1. So this should still be equal to 1. That rule shouldn't change. I want to go over one that has a higher power. Okay, so powers of I. Okay, so let me back up a little bit. We know that I to the first power, right? I to the first power, we're never going to see I to the first power, but I to the first power, we know that by definition is the square root -1. We know from the last problem, when we take I squared is equal to just plain -1. Now, if I keep on going, I'm going to get to 49, but I'm not going to have to go all the way to 49. But I just want to build some background here. So, say if I have I to the third power, I to the third power. Well, I to the third power is I to the second power times I. Right? The property of exponents still hold true. I squared times I to the first is I to the third. 2 plus 1 is equal to 3, adding the exponents. Okay, but what is this? I squared, by definition, I squared up here, I squared is -1. So this is really -1 times I. Well, what's -1 times I? -1 times I is -I. That's pretty weird. If you take I cubed is actually equal to -I. It simplifies to -I. Okay, let's go the next one. I to the fourth power. I to the fourth power, well, I'm going to say I to the fourth power is I squared times I squared. 2 plus 2 is equal to 4. But what's I squared? I squared up here, I squared is equal to -1. So this is really -1 times -1. What's -1 times -1? -1 times -1 is +1. So I to the fourth can be simplified down to a +1. Let's keep on going. Let's see how strange it gets. I to the fifth. I to the fifth, well, I to the fifth is I to the fourth times I. Well, the step above I to the fifth, I to the fourth is equal to 1. So this is just 1 times I. 1 times I is I. So let's see if we see a pattern here. Let's try one more, and then maybe you'll see the pattern. I to the sixth. Okay, again, we have 49 right here. Don't be scared. I'm not going to go all the way to 49. Okay, you're going to see a pattern. You might have seen it already. I to the sixth. I to the sixth is well, I to the sixth is I to the fifth times I. I to the fifth is, well, I to the fifth from the step above. I to the fifth is I. So this is I times I. I times I is I squared. I squared is -1. So let's look at the odd exponents. Okay, let's look at the odd exponents. The odd exponents. I is equal to I, obviously. I cubed is equal to -I. I to the fifth is equal to I. What do you think I to the seventh is? I to the seventh is just I to the sixth times I. I to the sixth is -1, so this is going to be -I again. So all the odd exponents of I, all the odd powers of I are either I or -I. Now, which one would it be? We don't want to guess, but we know that this is either going to be I or this is going to be -I. And I don't have to find what I to the 48th power is. What I can do is I can take I to the 49th, and there's lots of ways you can do this. I just feel this way is the easiest. I can take I to the 49th, and I can use I squared. I squared is the key to my method here. And if I take 49 and divide it by 2, I get a decimal, right? 49 divided by 2. If I put 24 right here, all right, 2 times 24 is 48, right? If I take 49 divided by 2, I get like 24.5. So this right here, 2 times 24 is 48. Well, how would I get 49? Well, I have to multiply this by another I. So this is now able to be simplified further, because what do I know I squared is? Well, I circled it up here. I squared is equal to -1. So this is -1 to the 24th power times I. A negative raised to an even power is always positive. -1 raised to an even power is always positive. So this is really just 1 times I. And 1 times I is just I. So what we put in the box here is just I. Okay, don't worry, we'll go over another one. But this is how I do it. I always break it up into powers of 2, because 2 is either going to go into this number because the number is going to be even, or it's not going to go into this number. If it doesn't go into the number, then I multiply it by an extra I. If it does go into the number, then I don't have to multiply it by an extra I. Okay, so let's look at another one here. Let's look at 18. Okay, another odd one. Okay, another odd one. So the odd ones are either going to be I or negative I. So here's how I do it. I take I to the 65th power, and I take 65, and I divide it by 2. I take 65 divided by 2. And you can just use your calculator. You can go 65 divided by 2, and just ignore the decimal. It says 32.5, so just put 32. Put 32 here. 32. Now, 2 times 32 is 64, not 65. So I can multiply it by another I. Now, this I is to the first power. So now I get something that's equivalent to I to the 65th. But why do I use I squared? I use I squared because it's negative 1. Negative 1 is easy to take a power of, because if it's a power of even, it's going to be positive 1. If it's a power that's odd, it's going to be negative 1. 32 is even, so this is going to be a positive 1 times I, which is equal to I. All right. Let's see. That's 18. Let's see if one more. See if I can do an even one here. Still odd. There's an even one. I to the 72nd power. So, I mean, this number here is either going to be even or odd. So the last 2 examples I did were odds. This one's an even one. Well, even ones are a little bit easier because you can divide by 2. So we can just make this I squared. What's 72 divided by 2? 36. I squared is negative 1. That's the key. The key to do it this way, the key step in doing it this way is to remember that I squared is equal to negative 1. You got to drill that into your head. Because once you know this, I squared is negative 1. As soon as you see I squared, you're going to think negative 1. And now negative 1 to the positive 36th power, an even power of negative 1 is just positive 1. So this is just positive 1. Even exponents are either positive 1 or negative 1. Odd exponents are either positive I or negative I. These are for even exponents. When you see this number here, even, and this is for odd. Okay, this is I raised to an even power, and this is I raised to an odd power. There's a little chart there that can help you out. Okay. 21. 21. Okay, these are called complex numbers. They're in the form A plus BI. A is the real number part, and BI is the imaginary number part. And normally it's written that way. It's written as A plus BI. A and B will be numbers, but this is the real part, and this is called the imaginary part. If you combine a real and imaginary number together, it's called a complex number. Complex. Okay. So the way to simplify complex numbers, when you combine binomials that are in this form, It's really similar to combining like terms. You only could add the real numbers to the other real numbers and the imaginary numbers to other imaginary numbers. And the imaginary numbers work the same as variables do. So this is just 2 plus 3, so it's 5. And then you have a negative I and you add a 5i. That's like negative x plus 5x, right? When you combine like terms, that's going to be just 4x. So that's the same over here. We just put, instead of x, we put 4i. Okay, this is the form you want to write it in. You don't want to write it as 4i plus 5. You want it as 5 plus 4i. Okay, always the real number first and the imaginary number second. Okay, so that shouldn't be a problem. There's no simplifying you have to do. You just have to just add them. Clear the screen here. 23. Okay. All right. This is one that we have to remember. They're both imaginary, so we have to convert them to their imaginary units first. So let's just do this in two parts. That negative is going to be a -1. And then I'm just going to do negative 50 first. 50 is 25 times 2. Okay, so the negative is going to come out as an I. The 25 is going to come out as a 5. And the 2 is left inside. Okay, so that's the first part. 18. So I'm going to add. This is 18 or negative 18. So -1. 18 is a 9 times a 2. I don't want to say 3 times 6 because I can't take the square root of either one of those, but I can take the square root of -1, so that's the I. I can take the square root of 9, that's a 3. And I have left the square root 2. Okay, so now that was done on purpose. The problem had a square root 2 here and a square root 2 here. So what we can do is one more step. This is kind of like combining like terms. 5i root 2 plus 3i root 2. We can combine these two. They're almost like coefficients now. We can combine those two. 5i plus 3i, that's just 8i. And root 2 is just going to be coming along in our answer. Okay, root 2 plus root 2, we do not add the numbers inside the radical. Root 2 plus root 2 is just 5i plus 3i root 2. So, I mean, if you had root 2 plus root 2 by itself, that's just a 1 right there, and that's just a 1 right here. That's just 2 root 2. Okay, kind of like x plus x is equal to 2x. Similar. Root 2 plus root 2 is 2 root 2. The root 2 kind of just acts like almost like the x's here. That was 23. 25. We're almost done here. I am going to be doing a live lecture this morning at 9 o'clock, and we're going to be talking more about this. You might want to view that as well before trying homework 15. Okay, here's a binomial that is squared. I like to do this using the box method. Do not square the first and the last. Use the box method. Use the box method. Use the box method. I said that 3 times because it's very important. 1 minus 2i squared is 1 minus 2i times 1 minus 2i. 1 minus 2i times 1 minus 2i. You need to think about it like this. 1 minus 2i, that should be an I. 1 minus 2i. So you have two binomials. When you multiply two binomials, you use the box method. So 1 times 1 is 1. Negative 2i times 1 is negative 2i. 1 times negative 2i is negative 2i. And negative 2i times negative 2i, you have to be careful. Be careful right here. Careful. Negative 2 times negative 2 is 4. I times I is I squared. What are you supposed to do when you see an I squared? You're supposed to think I squared is equal to negative 1. So this is negative 4. This is negative 4. Never leave an I squared. Always change it to negative 1. And now we can combine like terms. 1 minus 4. I do that first because it's got to be in a plus bi form. So 1 minus 4 is negative 3. And then negative 2i plus negative 2i is just negative 4i. Okay, so we write our answer this way. Okay, last problem. (26). We talked about rationalizing denominators yesterday. You have to be able to rationalize denominators that contain complex numbers as well. And so since I is equal to the square root of negative 1, this is not considered simplified. And so yesterday I talked about the conjugate. And I believe I used a big fat 1. And I'm going to do the same thing right here. 3 minus I. So I need to get rid of this this basically, I gotta get rid of this I here. This is not simplified because this I is in the denominator, and that I is equal to the square root negative 1. So I need to multiply it by, here's my big fat 1. You don't have to draw the big fat 1, but I just want you to understand that we're not changing the fraction. So I'm going to multiply by the conjugate of this right here. So the conjugate of 3 minus I, remember conjugates just change the sign in the middle. So it's 3 plus I. Multiply by 3 plus I on top and 3 plus I on the bottom. So I'm going to do the bottom first. 3 minus I times 3 plus I. Two binomials. You should be thinking box method. Box method. Box method. 3 minus I. 3 plus I. 3 times 3, 9. 3 times negative I, negative 3i. 3 times positive I, positive 3i. Negative I times positive I, be careful. Be careful. Negative I times positive I, that's a negative I squared. What's I squared? I squared is negative 1. What's a negative I squared then? If I squared is negative 1, if I squared is negative 1, what's a negative negative 1? Positive 1. So look what happens. These two go away. Those two go away. And then 9 plus 1 is 10. So we have 10 here. Now, on the top, we have negative 5 times 3 plus I. I'm not going to multiply out it using the distributive property. And I'll tell you why in a second. I'm just going to write it out. I'm not going to make this negative 15 minus 5i because there's one more step I can do. And if I multiply it out, I might not see this step. This number here, negative 5, goes into this number here. So 5 goes into 10. The negative stays there, but the 5 becomes a 1, and the 10 becomes a 2. So we have a negative on the outside, we have 3 plus I, and then we have it over 2. Okay, now I don't believe you have to distribute that negative. I think when we click this box, we have this fraction tool here. So we can go negative. I can make the parentheses. Can't make parentheses. Okay, well, if I can't make parentheses, I'm going to go ahead and just distribute this negative. Negative 3. That negative is going to be, this negative here is going to change this minus, this plus I to a minus I. So it's going to be minus I. And then it's over 2. That should give me the correct answer. What does it want? Negative 3 minus I over 2. What's it say? Let's see how it wants the answer here. Negative 3 minus I over 2. Oh, okay. So I wrote it. This is good. I wrote it as, I came up with this right here, negative 3 minus I over 2. They want you to, and this is kind of lame, they want you to write it this way. So they want you to write the 2 under the negative 3, and then they want you to break it up into A plus BI. That's, I'm sorry about that. That's kind of lame. So let me just show you how you want to write your answer. So negative 3 minus I over 2 is the correct answer. So what you do is you write that as your first part, negative 3 over 2, and then write this as your second part, negative, there's a 1 right there, so 1/2 I. Okay. If this were a handwritten assignment, I would have accepted this answer here. It doesn't look like the computer does that. Okay. You should be able to get through with homework 15. Tomorrow I'll have another Zoom session for questions that I'll record and put that recording on Canvas as well. All right.